what is it, or what are some of the main reasons that creatures evolved brains to begin with?
Well, we should start by just thinking about nervous systems, even before we get to brains. And almost all animals have a nervous system of some sort. Not quite all, there are a couple of exceptions, and sponges are the sort of well-known exception. There's also another odd exception. Why did animals evolve nervous systems? We don't really know, of course. It was a long time ago. We're probably talking uh, close to 600 million years or so ago. But I think a reasonable picture has a narrative a bit like this. We start thinking about just single-celled organisms, not bacteria, but single-celled eukaryotic organisms, larger and more complex cells that make up bodies like ours. Things like paramecia. Now, if you look at a paramecium through a microscope or other single-celled eukaryotic organisms, they're very active. They're not just sitting there on a plate like bacteria. They can move, they can swim, they attack each other, basically. So if you think about the world before animals even existed, a reasonable picture is one in which there were single-celled eukaryotes leading active, somewhat belligerent lives. Now, in that context, there's a size advantage. If you can get big, you become harder to engulf. A few biologists have thought that a size advantage was an important factor at this stage. John Bonner way back, Jochen Brox more recently. So you start forming colonies and collections of various kinds, partly for that reason, and perhaps also for other reasons. Now, because you're not plants, you're not algae, you're not able to photosynthesize, you're a different kind of being. In most cases, you're going to have to work out eventually how to act, how to do things in order to get food, and do so on this new scale of the larger multicellular organism. And I think that some of the early stages in animal evolution, if you look at the fossil record, the fossils we have suggest the animals were doing hardly anything. A lot of them were anchored to the seafloor, but this is before the Cambrian explosion. This is late in the period before that. They're the beginnings of what look like mobility and activity, the evolution of the left-right symmetrical or bilaterian body form that we have and octopuses have and most animals have. And in order to make action possible at all, you have to coordinate the activities of all these cells. And I think a reasonable picture of early nervous systems is one in which their initial role was coordinative, just pulling the body together, making action possible. Also responding to sensory events, because there aren't too many actions that are unconditionally good. Most actions are good in this circumstance, not good in that circumstance, so you have to work out which condition you're in, and that's where the sensors come in. So you have an integrative device connect to sensing, which becomes more elaborate, and that's a plausible story about the beginning of nervous systems, and it's a story about why they're present early and in almost all animals. A brain is a central nervous system, basically, or the central part of a nervous system, but the part where you've clustered lots and lots of neurons, nerve cells, together as a central controller, often between the eyes of the animal. And that kind of centralization has evolved independently a number of times. It's likely that the common ancestor certainly the common ancestor of all current animals that have nervous systems, it probably looked a little bit like a kind of jellyfish-ish being. No brain, no central nervous system, a more distributed nerve net. But also the common ancestor of all the animals that have left-right symmetry, us, octopuses, bees, and so on. It was probably looked a bit like a flatworm, perhaps, a small worm, maybe some clustering of neurons in the front. It may have had eye spots. And there are some biologists, Nick Strausfeld in particular at Arizona, who think there's reason to think that no, the common ancestor, that animal living 560 or so million years ago, may have had a brain-like concentration. He believes that because he thinks there's some similarities of design, if you look really closely, between our brains and the brains of insects that suggest some ancestral. There's an inheritance there from a common beginning. But it's a tiny brain. You know, we're talking about something very small. And I think the usual story about why brains become more substantial is just the demands of more complicated action. Integration is good, integrating different sensory lines, integrating your present experience with past experience, learning and memory. All those things are made possible by what we call a brain.